Alright, so let's do this Regents exam because I'm kind of bored and I don't know, I found these pretty helpful when I was studying for the Regents exam. So yeah, let's go through how to do these types of questions. This one is from August 2024. It's the most recent one as of right now because the January one hasn't come out yet. So yeah, which two particles each have a mass approximately equal to one atomic mass unit? Okay, so 1 AMU, we know that it's definitely not electrons. So cross these two out. And positrons, they're from nuclear chem, positron emission. So yeah, it's not really it either. We'd know that proton, neutrons, because in the nucleus of an atom, you have protons, neutrons, and they're each 1 AMU. What is going on? This autocorrect. Anyways, okay. As an electron in a hydrogen atom gains energy, moves from the first to the third, first to third, low to high energy level, hydrogen atom becomes an, okay, so it's telling you it's an atom, not an ion. And when it gains energy, it's going from the ground state to the excited state. Oh, I have an eraser. Going from the ground state to the excited state because it's gaining energy. Like, you can think of it like, I don't know, if you have something exciting, you get energized. Like, oh my gosh, so crazy. Oh gosh, that looks scary. Okay, two different isotopes of the same element. So the same element, what do they need to have to be the same element? The same number of protons. And they're two different isotopes, right? So they can't have the same number of neutrons because that would not be two isotopes. Not isotopes. Okay, so we have O2 and O3. This one has two oxygens, as the name suggests, and the other has three. So they definitely don't have the same molecular structure. They have different molecular structures. So you can cross 1 and 3 out right off the bat. And in molecules with different structures oftentimes have different properties. Because, you know, they're they're built different. So I don't know what else to say. I mean, they behave differently if they have different compositions. Okay. Describes the composition of a compound. Okay. So compounds, same element, is not the same as like a diatomic element. No. What is this autocorrect on about? Is not. Okay. So we can cross these two out. Um, and they wouldn't be physically combined because for it to be a compound, it needs to be chemically combined. Like say if you smush two things together, you smush, that's physically combining them, and they wouldn't be a compound. So they have to chemically interact to form a compound. Okay. This one, this one there's a rule that you just need to know, but if you didn't know that rule, you can probably do process elimination to find this one. So molecules, they're not really conserved during all chemical reactions because uh, molecules, they're changing during chemical reactions, right? Density, there's phase changes, so that takes out temperature too. Things during chemical reactions, the substances can go through phase changes, which would be not a conservation of density because say if I don't know, if a liquid's going to a gas, then it's becoming less dense and the temperature of the substance is increasing because it's gaining, well, usually because it's gaining kinetic energy and potential energy to go through that phase change. Okay. Metallic bonds. So, metal. This is a covalent compound or molecular compound. Same thing. It's two nonmetals. Oh, two nonmetals. And it's bonds, right? Okay. So this is an element that's neon. So there's no bonds going on there. This one is a ionic compound. So it's ionic bond. Only one here is this one. Fe is iron, which is a metal with metallic bonds. Oh, this is non-metal. Saying that as an element doesn't really make sense in this context. Cesium atom becomes a positive ion. Change in electron configuration and radius. What statement describes this change? Okay. It's becoming a positive ion. What happens when something becomes a positive ion? They have to lose an electron to become a positive ion, right? Because you're losing a negative charge. Losing a negative charge. Two negatives make a positive. So it's becoming positively charged. So it loses an electron. So when you lose something, your radius decreases because I don't really want to draw cesium because it's kind of big, but this is like some random thing. The middle is the nucleus. If this electron gets lost, the radius becomes smaller because you're losing that electron. So this shows the formation of a fluorine molecule. So I don't know if your teachers teach this acronym, but my teacher did. So breaking a bond absorbs energy and release. So forming a bond releases energy and breaking a bond absorbs energy. That makes sense because think when you have to break a piece of paper and you rip it, you have to use your hand. Oh, that's a really bad hand. This one's even worse. You have to put in your energy to break that piece of paper. So the paper is absorbing your energy to break. So yeah, barf. Break, absorb. Breaking bonds absorbs energy, and forming bonds releases energy. So here it would be a bond is formed as energy is released. Okay, so this one asks which in the ground state stable valence electron configuration. Stable means 8 electrons in the valence shell, which is the outermost shell. So this one you can just look in your reference table, honestly, and you would find that the answer is radon. Oh, I mean, you don't have to look at your reference table. You could just be like, okay, I know, so this one is group 1, definitely not, and this is a noble gas. So it's stable and has 8 valence electrons. Yeah. Which term represents the strength of attraction that an atom has for the electrons in a chemical bond? Okay, let's just go down the list. It's not entropy because entropy is like basically a measure of disorder or randomness or whatever you want to call it in a sample of matter. So for example, something with high entropy could be like a gas, high entropy. Yeah, so it's not that one. Okay, it's electronegativity because it's electronegativity just means how able is an atom in attracting electrons. So if you flip to table S and you look at the table thing, you would see that the element with the highest electronegativity is fluorine, and fluorine it is also located in the top right corner. Top right corner just means that it has the most protons in its row. It has 9 protons. And it has 2 shells. 2, 7. So this is actually very positive because it's 9 protons. Protons have positive charge. And 2 shells is relatively small. So this very positive nucleus is more effective at pulling in electrons because electrons negatively charged. So positive attracts negative. Yeah. Trace describes a sample. Okay, so this is this is sodium chloride and it's solid. So it's not a mixture because oh my gosh. It's not a mixture because it's just one thing. It's just salt. I mean if it were like sodium chloride and AQ, that would be a mixture because it's mixed with water, but it's not, so it's not a mixture. And it does have constant composition throughout, so it'd be 3. Substances contain only atoms with the same atomic number. Okay, so this is basically just asking for an element because only an element would have atoms with the same atomic number throughout. So this one would be selenium. If you wanted to go through this and double check, you could list all these out. This is the number 1, first element on the periodic table. This is number 7, not the same atomic number throughout, because 1 is not 7. Carbon is number 6, 1 is not 6. Hydrogen is number 8, 1 is not 8. So yeah, selenium. Differences in which property allow the separation of a mixture of 2-propanol and alcohol and water by distillation. Distillation is the process where you separate two things by their boiling points, by a difference in boiling point. It's like and then you put a heat source. It could be like fire or something. I don't know. Heat plate, hot plate, heat plate. And then this at the top is collecting whatever thing boils first. And then there's like a little tube connected to like a container to collect the stuff drips in. Yeah. If it were separating by solubility, it'd be like something, maybe sand and water. You could have like a sample of sand water that you pour onto filter paper and then drips water. And there's like a residue of sand on top of the filter paper because sand doesn't dissolve in water. It does not dissolve in water. So it would be the little residue on top. At standard temperature, how do the freezing point and boiling point of H2O compare to the freezing point and boiling point of 1 molar potassium chloride? So, potassium chloride, this is an ionic compound that is soluble in water. So it would be something like this. KCl. KCl, KCl, K. Oh, Cl, K. Something like this, I don't know. Compared to water, which would just be like this. So, in an aqueous solution with ionic salt, with a salt, the freezing point is lower because, okay, what it is when water freezes, it's really just going from like free-flowing H2O freeze to like an ice cube, which would be like where they're all sitting, well, not sitting, but you know, like not flowing ice. But when you have something dissolved in there, it makes it harder for the water to freeze. I'm just gonna use like a red color as the K's and the Cl's. There's stuff in between that is making it harder. Makes it harder for water to freeze. So you would need the temperature to be lower in order for the solution to freeze. So the first statement is false because it's saying that the freezing point of H2O will be lower. The freezing point of the KCl is lower. Not true. So we can cross out both 1 and 3. And to know the boiling point, it's also just a matter of intermolecular forces. So KCl has IMFs, which would increase the boiling point, increases boiling point of solution. Oh, what is going on? Compared to water. So, choice 4 would be correct. Water has a lower boiling point than KCl, but a higher freezing point than KCl because KCl dissolved things makes it harder for the water to freeze. So that means the freezing point of KCl is lower, and the intermolecular forces of attraction means that the the solution AQ this solution requires more energy to boil, so the boiling point will be higher than that of H2O. Form represents a form of energy, so thermal energy, but yeah, thermal energy is heat. Heat is not temperature. Heat is the transfer of temperature. Molarity is not a measure of energy. Molarity is a measure of concentration. Its moles over liters can be found on the back of the reference tables. This volume is not a measure of energy. What are these questions? Which sample of zinc has atoms with the highest average kinetic energy? Average kinetic energy, basically temperature, okay? So, which one of these has the highest temperature? Because 40 is greater than 30, is greater than 20, greater than 10. Under what conditions will a real gas behave more like an ideal gas? Okay, so this one, there's also an acronym for pressure, low, ideal, gas, high, temp. Or you can think of it like, if you're someone who, enjoys the heat, this is like an ideal vacation place, like the sun is shining, you're relaxing on the beach. Oh, this is a terrible person. Whoops. This is supposed to be a beach towel. You? Oh, not you, sorry. This is a bad drawing of a person. But anyways, high temperature, low pressure, because there's no stress, you're on vacation, everything is chill. So yeah, sorry. Low pressure, high temperature. Kinetic molecular theory of ideal gas. Okay. Ideal gases, not circular paths. They move straight random motion. Yeah, this one. If they have straight random motion, that means there's no attractive forces between them. Because if they were attracted to each other, they would be moving in circular paths. Did I scroll past? Oh wait, no. Reaction between two different gases is most likely to occur when the colliding molecules have proper energy. Oh, yeah. This is you. This is like muscle memory at this point. Proper orientation, proper energy. Um, I'm trying to think of an analogy for this. I don't really know. This is just like instinct at this point. Proper orientation, proper energy. Statement describes a chemical reaction has reached equilibrium. Reaching equilibrium rate of forward reaction equals rate of reverse reaction. So no, the reactants have not been completely consumed. The reverse reaction, no, no. Equilibrium, dynamic equilibrium. This doesn't stop. I don't like. The concentration product remain constant for, nope, that's not true. So yeah, concentration of the products and the reactants remain constant because the rate of the forward reaction is equal to the rate of the reverse reaction. So the rate of each side being formed is the same, so the concentrations don't change. An enzyme acts as a catalyst to speed up reaction, providing alternate reaction pathway. Okay. So heat of reaction actually has nothing to do with this. This is a simple. Oh, that was terrible. Okay, this is better. This is a potential energy diagram. Reaction. So this is the energy barrier that the reactants have to overcome. By speeding up a reaction, you would make this energy a little less, right? To make it easier for the reactants to overcome the energy barrier. So this might be what like a catalyzed one looks like. It will lower activation energy, E sub A. That makes it easier, right? I mean, if you increase the activation energy, that would make it harder for the reactants to overcome that energy barrier. That would definitely not speed up the reaction. Which element has atoms that can bond together to form chains, rings, or networks? This is orgochem. Carbon. So this can only have one bond. So you can't really make chains with this. The hunk. 1, 2, 3, 4. Carbon makes 4. Nitrogen makes 3. Oxygen makes 2. Hydrogen makes 1. Okay, so this one you would flip in your reference table. This is on page 8, table R, organic functional groups. Contains an atom of nitrogen. This is chloropropane. This is a halocarbon. Has a halogen but doesn't have a nitrogen. Propanol. This is an alcohol. Only has O, H, and C's. Pentanone. This is a ketone. And it only has C's, H's, and O's. Propanamine. This one is an amine, as you can tell from the name here. And amines are like this. So this one is the one that has a nitrogen. How many electrons are shared between the carbon atoms in a molecule of ethene? So ethene, you can either look at your reference table on page 7 in table Q, or you can know that ene, ethine. I don't know how to say this actually. Methane, methine. Methine? Okay. Yeah. Wait, how do you say this? Methane, methane, methine, ethine. That sounds weird. Okay. Basically, single bond, double bond, triple bond. was like F means 2. How many electrons are shared between the 2 carbon atoms in a molecule of ethene? So you can just know that this is a triple bond. Triple bond. Every bond has two electrons. 2 times 3 is 6. So reduction. Reduction, how I thought of it was reduction is excuse me, reducing oxidation number. So how do you make the oxidation number go down? Well, you gain an electron. Gain electron. Because say if you had something whose oxidation number was -2, and then you give it an electron, it'd be -3. So from -2 to -3, you're getting smaller, which would be a reduction. So yeah, gain an electron. Indicator methyl orange is red in aqueous solution, has a pH value of, so this one most likely be a reference table question. I mean, I say this every time, but if you know how to do this without looking at the reference table, that's good. Good job. But it's easier to look at the reference table. This is page M. I mean, page 6. This is page 6 on table M. Methyl orange. You can look at the range. It's red to yellow in pH 3.1 to 4.4. So if it's red, it's definitely smaller pH than 3.1. Which one of these qualify? Only this one. So yeah. This would be like super yellow. This is so basic. Yellow. This would be yellow. Yeah. That's nice. Which radioactive emissions are listed in order from greatest penetrating power to least penetrating power? Okay. Wait, is there a page for this? I guess not. Oh wait, no. Yeah, there's a page for this. So this would be page O in page, oh my gosh, what am I saying? Table O. Table O, page 7. You can look and see that the alpha particles are the biggest. So if the alpha particles are first, then it's not right. The beta particles are also pretty big. The alpha particles are the biggest though. Alpha, biggest. So they have to be at the end. So it'll be this one. What is one benefit of a nuclear fission reaction? I don't know if this really counts as a benefit. I mean, that's just like a characteristic. What? That's definitely not a benefit. Not what benefit? Exposure to radiation, not good. In these types of nuclear reactions, like these reactions make a lot of energy. So that is definitely one benefit. Very efficient. Which statement compares the relative amounts of energy stored? Okay. So we just talked about how nuclear reactions more efficient. So look at this one. Nuclear reaction releases much more energy than normal chemical reactions. Density of a sample, Fe based on table S percent error. Okay. So table S percent error. Go to your reference table page real quick. See that the density of this thing is actually 7.87. 7.87. And then you can go onto the back of your reference table, table T, to find the percent error formula, which is measured minus accepted over accepted times 100. So this would be 7.57 minus 7.87 over 7.87. I got negative 3.8%. This one asks, based on table S, which general trend is observed as elements in group 17 are considered in order from increasing atomic number from fluorine iodine? Okay. So this, you can just compare the boiling points of these elements. It's on table S, and you would find that it's increasing boiling point every row down you go. So yeah. Reaction. Which type of chemical reaction is represented? Okay, this is a single replacement because this replaces the Fe2 to be with O3 here. And now on the other side, the Fe is alone. So it's single replacement. If it were synthesis, is like A plus B makes AB type of thing. Decomposition, AB makes A plus B. Double replacement, AB plus CD. Something like that. Now this is like A plus BC makes B plus AC. Yup. ISTP. Which property can be used? Rigid. Okay. So definitely not phase because they're both solids. At STP, this means that, oh shoot, this means that the temperature is at 0 degrees Celsius. Wouldn't be this one. 2 gram, wouldn't be this one. It would be solubility because NaCl, table salt, soluble in water because Na group 1 ions all pretty soluble, and according to halogen also soluble, but Ag is the exception. If Ag is paired with Cl, it becomes insoluble in water. So you would see precipitates form when you try to dissolve silver chloride in water. Next one. Which particle model diagram represents a sample of neon at 35K and 1.0 atmosphere? So, neon, this is a gas most of the times. So you wouldn't really see it like be this or this. And neon isn't diatomic. Not diatomic. So it can only be this one. There are only so many diatomic elements. You should probably memorize them, but you don't have to, you know. It's good too though. 7H2, or Dr. Brinkelhoff. Brinkelhoff. Wait, that's a bad F. These seven diatomic elements. Ne is not one of them. So yeah, this one, it's like a gas. It's pretty cool. Most polar bond. Polar, big difference in electronegativity. You can look on table S to find the electronegativities. Hydrogen is 2.2. So you just have to find the bigger of Cl. Excuse me. Of Cl and Br. Cl is 3.2. Br is 3.0. 3.2 minus 2.2 is 1.0. 3.0 minus 2.2 is 0.8. 1.0 is greater than 0.8. So HCl would have the most polar bond out of these four. What is the amount of heat that must be absorbed to increase the temperature of a 130-gram sample of water from 20 to 50? So this is Ti, Tf. This is the Q equals mc delta T. Q equals mc delta T, where Q is the amount of heat, which is what the question is asking. Q equals mass of the water, 130 grams. C is the specific heat, 4.18. Delta T is Tf minus Ti. Tf minus Ti is 50 minus 20, which would be 30. Got 6. This was the answer in scientific notation, be number 2. Sealed rigid container contains 50 milliliters of argon gas. Second, sealed helium gas. Which conditions of volume, pressure, temperature second would result in the number of helium atoms being equal to the number of argon atoms in the first container? Okay. So it would have to be the same conditions because argon, helium, pretty similar. They're not diatomic. It's just argon and helium. So the similar pressure and volume would result in the number of helium atoms being equal to the number of argon atoms. You see, these two conditions are identical. So yeah, that's pretty cool. Ugh, my leg's numb. Which equation represents a physical equilibrium? Not chemical. So this would be like phases, right? So it's not this one. Not this one, this is chemical. Be this one, because it's the rate at which carbon dioxide is going to solid carbon dioxide is the same as the solid carbon dioxide going to gaseous carbon dioxide. So this is physical equilibrium. Change occurs when the temperature is increased. Temperature, this is basically kinetic energy. So if you're increasing this, think of it like a seesaw. You're weighing down this side. So it's more prone for the reaction to shift left. The reaction is more prone to shifting left. Cross out these two. Be this one. Because if you're shifting left, you're consuming this. You're using more of this to make these two. So these two, their concentration will increase while this one decreases. Perfect. This is the entropy from earlier. Highest to lowest. This is a decrease in entropy. This is a decrease in entropy, decrease in entropy. This is an increase in entropy because liquid going to a gas is more random. So you can think of it like this. Liquid, oh, this is Cl, diatomic. But a gas, a sample of chlorine gas might be like very scattered. There's an opening, so maybe the gas escapes. So yeah, very random indeed. Unsaturated hydrocarbon. Saturated? Basically, single bonds. It's like the hydrocarbon is holding the maximum number of hydrogen it can possibly hold on to. So it's not this one. Not this one. And it will be this one. Because you see the double bond here? This doesn't matter because it's not bonded to a C, it's bonded to an O. If that's confusing, just sorry. Complete equation fermentation. Okay, so, if you know some information, you might know that fermentation is going into alcohol and CO2. Which one's sugar? This one's sugar. So, yeah, pretty perfect. I mean, obviously, this is not the only way to do it. You could technically like count all of these. So there's 2 C's here. How do I want to write this? 2 C's, 4 O's. And here you have 4 C's because you have 2 in one of these, and you have 4 in 2 of these. You have 6 H's in 1, 12 H's in 2. My pen's not working. My pen's working. And 1 O in 1, 2 O's in 2. So you can add these all up and see 6 12, 6. So this is like a longer way to do it, but if you know this, it's pretty simple. Wow, what did I just say? Obviously, if you know it's pretty simple. Oops. Okay. Work, bro. I don't know what happened there. We just did this one. Combustion reaction. Products always H2O and CO2. Which one's H2O and CO2? It's number 2. H2O, CO2. So, excuse me. So the charge is always conserved in a chemical reaction. This was a problem from earlier. This is, well, based on a problem from earlier, actually. There's this other one that was like, which quantity is always conserved in the chemical reaction? That answer was charge. So if you're losing 2 moles of electrons, you better gain 2 moles of electrons. Otherwise, where are the electrons going, right? So, okay. So this one, concentration of potassium in parts per million. So here they already give it to you in grams per 1,000 grams of water. So you can, what I would do is I would set up a proportion, but you also don't have to. There's a lot of different ways to do this. So you get that. And then you divide. And you get that. It's 394 parts per million. What happens to the potential energy of water molecules as they evaporate? So evaporation is phase change from liquid to gas. And this is like a visual. And just pretend these are water molecules. They're like going from this to this. Gases have more potential energy than liquids, PE. So going from a liquid to a gas would be an increase in PE. So you can say the molecules gain potential energy increases as it evaporates. Something along those lines should be okay. State how concentration of ions in a sample of seawater changes as water evaporates from. Okay, so if water is evaporating from the solution to surroundings because it's becoming water vapor, the solution would increase in molarity because there's fewer liters of water, of liquid water. So you would have a smaller denominator, increase in molarity, which is concentration. The brackets just mean concentration. So you would say that concentration goes up, concentration of the ions increases as water evaporates, something like that. Using the key in your answer booklet, draw at least 2 water molecules in the box, showing orientation of each water molecule towards the bromide ion. So I don't have the answer booklet. I'm kind of lazy. I don't want to look it up. So I'm assuming it's probably something like this, where you have a bromine ion. And water is usually like this. Usually, these little things are the hydrogen. this big thing is the oxygen. So you have H2O, right? So you have the big bromine. This is an anion because it has a negative charge, anion, a negative ion. And then in water, there's hydrogen and oxygen. And since water is a polar molecule, has an asymmetrical distribution of charge. So if you look up the electronegativities in the reference table, you would see that hydrogen is 2.2, oxygen is bigger than 2.2. So the hydrogen would be the partial positive, while the oxygen would be partial negative. So since opposites attract, opposites attract, you would draw the hydrogens pointing towards the bromine ion. Something like this. Doesn't tell you how many you need to draw. So I'm just gonna, okay, this is really poorly drawn. Water does not look like that. I don't know if you need 4, but I just did 4, because why not? What is going on? What? Where'd all my stuff go? Whatever, we just did it, so it's fine. Identify the positive ion in the solution of hydrochloric acid. Okay. Wait. So HCl is hydrochloric acid, they tell you here. And it has H plus ion and Cl minus. So if you have like this, it's single arrow because it's a strong acid, completely dissociates. You have H3O plus and Cl minus. So the positive thing here will be these, right? But they're like basically the same thing. You can use them pretty much interchangeably in Regents Chem. So you can say, you can like write these chemicals, you can just write these formulas, but you can also give their name. So hydrogen ion, H3O plus is the hydronium ion. Hydronium ion, this name is in table E, polyatomic ions, I think. Complete the equation in your answer booklet for the reaction that occurs. Okay, I don't have the answer booklet again, but it's okay. It's just a titration. So I'm assuming they're just asking you for like a, like what happens when you mix the acid and the base. Oh, like the products of this reaction. Okay. So you have a strong acid, hydrochloric acid, and you have a strong base, potassium hydroxide. So in every acid and base, like these types of reactions, you always make water and you always make a salt, an ionic compound. So you're using this and this for the water. So what's left over? KCl. So this is your salt. Should probably write the phases too. I always forget. Good habit to write the phases. So these two would be your answer if they're asking for the products. Show numerical solve for calculating molarity using titration data from the trial tip. Circle this. Okay. Okay, so they give you this molarity here, so you can just use the MAVA equals MBVB for concentration. The concentration of HCl is what we're solving for, so we're going to have MA here. VA would be the number here because it says the volume of HCl, which is the acid. You can multiply it by 10.0 milliliters equals MBVB. The molarity is given here for KOH, and the volume is also right here. You plug this into your calculator. You get that MA equals 2.4 divided. Oh, wait, no. They're asking for the numerical setup. You don't have to do this. You can just leave it at this step. This step is fine. I just started solving for it. Oops. Ignore that. Explain in terms of experimental design why it is better to use data from multiple trials. Titration. Okay, so you just have to like write a quick little blurb here. What I usually go with for these, like, in terms of experimental design, why it's better to use multiple, I just say that you can average the results, okay, to help decrease effect of random error. You should probably like write the word decrease out here, actually. Yeah, I don't like writing, so I'm just using arrow. But on the Regents exam, you should probably write it out. State the neutron to proton ratio in the helium product of the reaction. So gives you that it has 2 protons, atomic mass 4. So we know that only the protons and the neutrons are each 1 AMU. Since we have 2, 4 minus 2 is 2. So you have 2 protons, 2 neutrons, and we want to be sure to answer the problem, so we have to state the ratio. So you can say either 2 to 2, however you want to express it, 2 over 2, 1 to 1 ratio. These answers, I think, are all acceptable. Based on table N, state the decay mode of tritium. I don't have the reference table right now. I have it now. So you would look to page 6 of your reference table for the decay mode of tritium, which is just H with a 3, hydrogen 3. And you will find that it has beta decay, like this symbol. And then determine the time required for a 1 gram sample of tritium produced to decay until 0.25 grams of the sample remains unchanged. So we start with 1. Well, after 1 half-life, you have 0.5 grams. 2 half-lives, 0.25 grams. So 2 half-lives have to elapse. The half-life of tritium, according to the reference table, is 12.31 years. 12.31 years times 2 is 24.62. And then complete the nuclear equation in your answer booklet for this reaction by writing a notation for the missing reactant. So I'm guessing they're talking about this equation. I'll just do it here. So basically what you have to do is like, you see here, it's 3. This is 0. So this over here, the bottom has to be 3 to make it all add up. And this, 3 plus 4 equals 7. There's already 1 here. 7 minus 1 is 6. So this here will be 6 and 3, like that. And the third element on the periodic table is lithium. So it'll be lithium 6. You can write it like this, or you can say lithium 6, Li6, whatever works. Alright.